Namaste. Let us start the final lecture of this course on physics of nanomaterials. You must have realized by now the importance of nanomaterials and the growing use of nanomaterials in various devices and the devices which are driving the field of nanotechnology. These devices are in and around us even if we do not realize it. From sensors to batteries, from toys to coatings, from memory readers to nanofluids, and so on and so forth. We have also understood how to fabricate nanomaterials, and we are studying the characterization tools to investigate the physical properties of nanomaterials in this week, and the discussion started on this topic from the previous week. So, today let us have a discussion on the use of IR and Raman spectroscopy measurements in the area of characterization of nanomaterials. We will introduce these topics today. We will talk about the instrumentation, how simple these instruments are. Once we are able to control the fabrication of the components which are used to make these instruments, then the physics associated with the data that comes out of it is very interesting. You already know about it, and from there you can back calculate the properties of nanomaterials. If you want to ask a question, the first question would be, what is spectroscopy? It is defined as the field which is discussing or describing how matter interacts with electromagnetic radiations. The interactions can be of various natures. You can have absorption, you can have emission, you can have scattering, or you can have hybrid features. But this is directly related to the material which is being investigated. Hence, it provides the fingerprint of the material which is being investigated. Mostly, this technique is a non-destructive technique, but there can be some samples which are very soft and they can get damaged if you have continuous IR falling on these samples, but mostly it is a non-destructive technique. So, you have light which falls on the sample and you have a spectrometer which is there that gives you the spectrum, and then you can have the intensity versus wavelength curve, and that will give you the fingerprint. So, it is as simple as this. You have various types of spectroscopy. You can have electromagnetic radiation based analysis, which gives you various types of techniques. You can have emission and absorption based studies, that gives you various types of techniques. You can have particle interactions and then analyze, you have different types of results coming out, or you can have specialized spectroscopy, for example SERS, that is the surface enhanced Raman spectroscopy. You can have Fourier transform infrared spectroscopy, or you can have time resolved spectroscopy. So, by having various combinations or by taking one of the interactions in detail, you can have different types of experimental tools which are designed and then they are used to investigate the properties of the nanomaterials which you are synthesizing. But the principle remains the same. There is a source, there is a sample, and you collect the data and then plot the spectrum, that is, for example, intensity versus wavelength curve. In a typical IR spectroscopy, you have the study of the absorption of IR by molecules. Now, for a given molecule, these are going to be fixed. So, it is used to study the molecular vibrations and provide information about the chemical structure, the nature of bonding and functional groups which are present. Typically, IR range lies between microwave and visible light in the electromagnetic spectrum. So, now you have a source which is giving an IR radiation which is falling on the sample. As an output, you collect the transmittance or absorbance curve as a function of wave number, and that will give you the molecular fingerprint of the sample, because every molecule will have a unique IR spectrum. This is a typical FTIR spectrometer, which is taking the Fourier transform of the spectrum which you obtain, and this gives you clear pictures of any modifications in the spectrum which are there, because you have taken a Fourier transform and smallest of changes are clearly deciphered in the spectrum. So, what will you do? As you know, the chemical bonds are not rigid. They behave like springs, and hence you will have a stretching mode and a bending mode. Now, only those molecules that have a dipole moment, they respond to IR radiation. The photon energies associated with IR spectra induce a vibration excitation of the covalently bonded atoms and groups. So, now when you have this light photon falling, or the radiation, the electromagnetic radiation which is falling, it gives you energy and therefore, that drives an excitation. So, that kind of there is an excitation of the vibrational modes. Now, these causes change in the dipole moment of the molecules, and the frequency of the radiation, when it matches to the natural vibrational frequency of the molecule, you have the high intensity profile or peaks which appear, and the photon energy is absorbed and missing from the original IR spectra. This is what we take as the background measurement. So, you can have two types of modes, stretching or bending. You can have symmetric stretching modes or asymmetric, where one of the bonds stretches while the other compresses. So, one bond stretches, the other compresses. In the bending modes, you can have the scissoring, rocking, wedging and twisting modes, and you can clearly see the nature of the atomic displacements in these kind of modes. And as the bond lengths change, you will see that they will have different absorptions of from the incoming IR radiation, and therefore, the signal would be different. So, you use the IR source, use the typical optics, you have the beam splitter, you have the fixed mirror, you have the movable mirror. Remember, it looks very similar to the Michelson's interferometer, and you have the sample, and if you have the transmittance data, then you have a detector which is connected to the processing unit. So, this is a typical spectrometer. You use a halogen lamp which gives you the near IR spectroscopic data. If you use synchrotron radiation, then you will get far IR as the incident radiation. If you use silicon carbide based, a common and a robust source, then you will have the black body like IR spectrum suitable for mid IR measurements. If you have the Nernst glower, this source is again for mid IR applications and is a ceramic material that emits IR radiation when heated. So, depending upon which energy region you are investigating, you will choose the measurement or the place where you will be carrying out the studies. So, this is a typical Michelson's interferometer which is used. Now, you have a semi-transparent mirror that divides the IR beam. So, you have the beam splitter into two separate beams. Now, one beam is directly reflected by the stationary mirror and the other is reflected back by the moving mirror. So, one beam goes in this direction, the other goes in this direction, and then what happens when the reflected beam returns from the beam splitter? They are combined to create an interference pattern. So, you have two beams and then you have the beams which are from the same source. So, you have a monochromatic beam, then you have two beams which are passing through and then falling on the sample and giving out the interference patterns. So, typical Michelson's interferometer. You have various types of detectors which are used for analyzing the spectrum. You can have thermal detectors, you can have photon detectors, or you can have imaging detectors. Each have their own advantages and limitations. So, depending upon your requirement, you will now have an apparatus with the required detector. If, for example, you look into the various functional groups, for example, if you are talking about CH vibrational modes, they appear between 2850 to 3300 wave number. If you have the carbon double bonded oxygen modes, then they are appearing in this. If you have the alcohol modes, then they are coming in this region. If you have acidic nature of the sample, then they are appearing in these regions. So, just by analyzing the IR spectra, you can easily find out the nature of the bonds which are there, and you can characterize the materials very easily. This is just an IR spectra of an ethanoic acid. You can use these techniques for biomolecules, metal complex, drug cell interactions, polymer matrices, structural determination, functional group identification, or impurity determination on the samples. As you change the size of the sample, what happens? The bond lengths change, and therefore, you will start seeing change in the vibrational peaks. So, that also you can calculate easily. The nature of stretching and bending modes will change, and hence you will be able to directly estimate what would be the impact of the incoming energized ions or radiations on samples as you modulate the size of the particles in the samples you are synthesizing. You must have understood that there are advantages and limitations. So, FTIR is simple and sensitive, provides fast data, very simple to operate, and the physics behind is already well understood. But limitations is molecules must be IR active. You do not get information about the elements which are present, and the material should be transparent to certain extent to give you a reliable data. The other technique which is there is the Raman spectrometer. It is based on Raman effect. It is a non-destructive technique used for vibrational, rotational, or low frequency mode determination in systems, and is extensively used for carrying out all kind of studies which we had discussed in the case of IR. For example, you can use for environmental monitoring, interactions, biological applications in material science, forensic science, or food analysis. So, you have large number of applications of a Raman spectrometer. So, just by having one instrument or an experimental tool at your disposal, you can find its application in so many industries. The principle is very simple. It is based on the principle of scattering of an incident beam on the sample, and you can have both scattered signals which are elastic in nature, or scattered signal which also have inelastic component, and you will get Stokes and anti-Stokes lines. And then by investigating these Stokes and anti-Stokes lines, you can determine the nature of the samples. So, if you have these Stokes, anti-Stokes, or Rayleigh scattering, you can easily find out the curve, which is, for example, you have the incident radiation, then you have lower frequency coming in from the Stokes scattering, and higher frequencies coming from the anti-Stokes scattering, and that means the nature of transitions which are there are of different character, and that is defining the point where the excitation and de-excitations are taking place. So, from which energy level the excitation is taking place and to which energy level the de-excitation is taking place defines your Rayleigh, Stokes and anti-Stokes scattering. Simple technique once again, you have the laser, focusing system, sample, collection system, filtering, simple monochromator and a detector system. You get, for example, you have the Raman spectra for graphene oxide or a composite of graphene oxide and Mn3O4, and you can easily get various types of modes, the D modes, the G modes, or you can have the A modes or E modes in the samples, which will tell you the nature of bonds which are forming in the samples. And we have already discussed that you have large number of applications. So, as the size of the material changes, the functionality of the material changes, the nature of Raman modes will change. If you have expansion or contraction, either you will see mode softening or mode hardening, and then you can easily find out what is happening to the unit cell of the sample, and as the unit cell parameters change, the energy levels or the free electron model changes, you have the change in the band diagram. As the band diagram changes, you have direct impact on the physical properties of the materials. So, spectroscopic measurements like Raman and IR or FTIR are also two of the commonly used techniques to investigate the properties of nanomaterials and how the vibration modes change in these materials as you reduce the size of the particles. These are some of the references which would be very useful for you to have more information about these two techniques. And I hope that you enjoyed this course on physics of nanomaterials. It's a vast field, it's a continuously evolving field, and you will find newer phenomena appearing as time passes, and you will have to keep yourself updating and updated with the latest developments in the field of nanomaterials and nanotechnology if you want to be relevant and contribute to the ever growing use of nanotechnology for our society as well as high end applications. I thank you very much for enrolling and for attending the lectures of this course, that is physics of nanomaterials, and I hope you enjoy the lectures. If you have any queries, please feel free to write to us or put it on the forum, and we will be answering to your questions on regular basis. You can also ask me questions during the live sessions, which would be organized in due course of time. Thank you very much.